We're going to look at some optimization problems. Namely, we're going to look at one involving a box. Why not, right? The actual problem is going to be listed in the description for this video, so you can get it from there. And I'm just going to give you the basis for the problem. So you might want to just pause for a second and read through that problem in the description to make sure you have an idea of what we're doing before I start explaining this. It might help a little bit. The basics of it is that we're going to create a square-based box. So there's going to be a box with a base that's going to be square. And we want the box to have a volume of 4 cubic feet. Now, what we want to do is minimize the surface area of the box. The actual problem, what it says, is we want to make it the most economical box we can, which means minimize the amount of material we're using to make this. We have this criteria that the base is square, which is actually going to be very useful to us. So let's start with some of the pieces that we know we can work with. Namely, let's figure out if we can figure out our primary equation here. Our primary equation had to do with making the box the most economical it could, which means reducing surface area. So surface area, there's our primary equation, right? So what's this going to look like? Well, we know that we're going to have a side of S, X, W, whatever you want to call it, and then another side of S over there. And then we're going to have the height, right? We already have S's there, so maybe instead of using S, maybe I use something else, maybe like, I don't know, L. Okay, to make it a little bit more distinctive. So I have L squared times H. Now, that's fine and dandy. But once again, with our primary equation and optimization, the thing that we worry about the most, or the biggest problem we're going to have or run into, is when we have two variables that are essentially independent, and then this one dependent variable upon both of those. I'm doing a little bit of pseudo discussion there, but that's okay. What I need to do is get rid of one of these variables. I could do this implicit differentiation, but the problem is going to be I'm going to have multiple rates in there, and I don't want multiple rates. I just want one, and I want to be able to set it equal to 0 because that's the whole idea of doing optimization. So what do? Well, the thing I got to remember is that over here, this is equal to L squared times H. Oh, I did something wrong here, didn't I? This is L squared plus L times H times 4, isn't it? There we go. That's better, right? Okay, so my volume is L times H, or L squared times H. My surface area is this. Now, this is going under the assumption that this doesn't have a top to it. Okay? That's what we're going with right now. This is an open top box for this one. If it was closed top, we would just take this top piece right here, the L squared, and we would times 2. So it's a very simple adjustment on that one. But just for the sake of what we're doing here, we're going to make this an open top box. Now what? Well, we got this equation over here, right? We have this equation over here with two variables in it. So can we solve this one for something? The thing we want to do is figure out the most economical way of building the box. We want the dimensions. So what I'm going to do with this thing is I have 4 equals L squared H. So I'm going to solve for H. So I have 4 over L squared equals H. Now I can rewrite my surface area equation as L squared plus 4 over L squared times L times 4, right? Well, that's nice. Okay, everything's got the same variable. Now, first thing we do in optimization. I want to pause, try to work in front of me a little bit here with this. What do? Well, we need a critical number. Where do we get a critical number from? From setting the first derivative equal to 0, which means we need the first derivative, right? So I'm going to do S A prime here, which would be 2L. Oh, you know what? I could have made this algebra a little bit easier on myself. So this little section right here, I can rewrite that as 16 over L, right? If you don't see that, pause a little bit, work through it, make sure you can see that. But that's going to make my life a little bit easier. And then I can think of this as being 16L to the negative 1. That's going to make the derivative easier. There we go. A little bit of algebra helps, huh? So that gives us negative 16L to the negative 2. All right. Now, next step, set it equal to 0. That's right. So we get 2L plus negative 16 over L squared. I'm going to switch it back to that form because that's going to make the next step a little bit easier. So I got 16L squared equals 2L. So what I'm doing here is I'm trying to get all the variables in one spot. These aren't like terms. I can't combine them like that. But what I can do is I can move this one over to the other side, and I can multiply both sides by L squared, and I get 16 equals 2L cubed. If you don't see that, pause, go look at it, okay? Divide by 2, I get 8 is equal to L cubed, which means, take the cube of both sides, L is equal to 2. Look at that, 2. That's an awesome answer, right? Okay, a lot of 2's in this problem, aren't there? So we have one of the dimensions. We know that L here equals 2 equals 2. Now we just need to figure out H. And luckily we have this nifty little equation here that allows it to be able to figure out what H is. So this is going to be 4 over 2 squared, which is H. So that tells me that H is going to be 1. H is 1. So what are my dimensions, right? If we want to wrap this up and get that taken care of. So my dimensions here are 2 feet by 2 feet by 1 foot. There you go, okay? I hope this was useful. Hope that you found some explanation here that you were searching for, and you understand optimization a little bit better. We actually forgot something. What did we forget? Well, we found these values, and we made an assumption, didn't we? The assumption we made was that this was actually the minimum amount of way we could do that process, right? It's the only critical number we have, right? That's what this is. This isn't a maximum. This is a critical number. How do we test the critical number? Well, here is our derivative, right? So we can plug in values on either side of 2 into my derivative and see if it goes from increasing to decreasing or decreasing to increasing, right? So let's just pick values on either side of 2. That was my value of L, was 2. So let's pick 1. So let's let L equal 1, and we'll let L equal 3. And we'll just plug them into this thing right here and see what happens. So when L equals, and we're looking for the value of the surface area, whether it's positive or negative. So I plug 1 in, I get 2 plus negative 16, which is negative, which means the function is decreasing, right? Plug in 3, so that gives us 6, and this is 16 over 9, which is less than 2, so this ends up being positive, which means the function is increasing. If you didn't catch all that, stop and pause the video, plug in those values, plug in 1, plug in 3. You'll see that you get positive negatives. Now, if you're switching from a negative to a positive, you're switching from decreasing to increasing, it means the graph is going down and then comes back up, which means that spot right there where L is equal to 2 is where the minimum occurs. Okay? That's not the minimum, that's where it occurs at. So now here is our proof, if you will, not a mathematical proof, but proof that it is indeed the minimum value. Now we're done. Now we can go back and say these dimensions we found give us the minimum surface area, which is going to make the box the most economical it can. All right, so take care. Reach out with questions and comments as you have them about this, and always math on, right?